Today I'm going to talk about power and efficiency, section 14.4. Okay. Uh, just a few things when typically we take a look at the slides following the author's approach is talk about applications first. That's like, what's the purpose of doing this and looking at it? Um, so far we looked at energy, sort of working energy, sort of standalone. Now we want to talk about power, which is essentially work and energy per unit time. Okay. So here's an example. If you're looking for, let's say, um, relationship between the force and the power of a motor lifting an elevator, right? So you might want to figure out what that power is that you need to lift an elevator at a specific speed. Okay. So just for that example, okay. Here's the second one, and the same thing. We want to relate like the how fast the truck can go related to how much power the engines give, how much the power the engine can put out, and the inclination of the hill. Okay. All right. So there's a couple pieces of this. One is the idea of efficiency, and we're going to look at that and knowing how much like what's the efficiency of like an engine when you actually have like if you think about it, how it actually starts out is you have energy in the fuel, and that energy is, that fuel is used to, you know, uh, power your engine or whatever, has explosions or whatever, converts the heat, or it's burned and converts heat over to motion. And there's a certain efficiency related to that in terms of like how much of that energy from the fuel actually makes it to power to transmit it to the actual wheels of the truck. Okay. So we're going to look at some of these. So knowing engine power and speed of the truck, can you figure out the maximum angle, right? So some of these relationships we want to look at: speed, power, efficiency, force. Okay. Okay. So we start off with this idea of power. First thing is power is basically, if you think about it, it's just the derivative uh, of the energy with respect to time. Okay. So we had looked at it. We had this delta U, which represented our incremental energy, right? It's dr. Um, if we forget the derivative of it, we can find like that instantaneous power because it's power is in basically energy or work per unit time. Okay. And if we do that, all essentially here's our force dotted with delta R, or dr. Um, we divide it by delta t. So all I'm doing is taking it and, of course, substituting it for du here. And then what we recognize is essentially it's the same thing. So if you're dotting it, you do the inner product or scalar product is another term that's used. It's the same thing essentially as, you could break up and pull out the force. And then now you have delta r over dt, which is just our velocity, okay, as a vector. So both are vectors. Okay. So that's essentially it. Essentially, what we come up with is it's just the force dotted with a velocity vector. Force vector dotted with a velocity vector, okay? Which is essentially, if you think about it, what is that really saying? It's like, you know, the x components multiplied times the x components, the y components multiplied times the y components, and the z components multiplied times the z components. If you're doing, if you're in the Cartesian coordinate system, okay? All right. So we can also write it this way. Okay. So basically, it's the tangential component or the force along the line of action, or the other way to think about it is the projection, right? This is kind of our projection. So it's like projection of the force along the velocity. Okay, direction of the velocity. All right. So that's another way to represent the power. Okay. And the units, USCS system is joules per second, watt or joules per second, and joule, of course, was a nanometer, um, and then divide that by seconds, come up with the same thing. The other one the FPS or USCS system is expressed in horsepower or horsepower typically, which is foot-pounds per second, okay, which we can convert. So 550 foot-pounds per second is actually equal to 746 watts. So in the USCS system or FPS system, we'll see horsepowers or foot-pounds per second as the units. Okay. The next thing is we're going to look at is efficiency. Okay. Now, efficiency is basically defined as just saying whatever power you can get out divided by whatever power input. Okay. And what you're always going to find in this case is that efficiency is going to be less than one. Okay. And the reason for that is we're going to lose energy in form of heat, right? And some other so we're actually losing it to overcome friction, which generates heat, and then we're always going to be less than one in terms of our efficiency of any machine. Okay, just in terms of the procedure for analysis, we may need a free body diagram for this. Okay, and then we just find the velocity of the point at which the force is applied, where we care, and we use whatever equations, kinematics or kinetics as needed. Okay. We just multiply that force by the component of the velocity in the direction of F, okay, which was this, which is essentially our projection of F on our velocity. And then sometimes we may need to go and find it this way, doing the derivative, okay, find the derivative of that work if it's a function of time. And also after that, it's in terms of like either we're given the efficiency or we can determine the efficiency, of course, by power input related to the output. Okay. Okay, we'll take a look at an example. So we have a 50 kilogram block hoisted by pulley system and motor. Motor has efficiency of 0.8. Okay, and at this instant, cable point P has a cable velocity of 12 meters per second, which is increasing at a rate of 6 meters per second squared. Okay, so you have some acceleration associated with that. And the last thing, we neglect the mass of the pulleys and the cables. Okay, so if we look at this problem, we're given some information here. It's like, oh, okay, so we're given the efficiency, and we know efficiency is power out divided by power in. And the end result is here. What we're looking for is the power supplied to the motor. So we can use this information, calculate the power out, and then we use that power out with the efficiency, and then we can figure out what the power in is for this motor provided at that moment. So some of the things to think about here, if you're looking at how far this goes up, we have a pulley, so it's actually this is all the same cable. And we have essentially, for this to go down, 1 meter, let's say, this would only go up half a meter. This block would only move up half, right? So we need to think about that in terms of relationship between position. So for this block moving, the motion of the block or the displacement of the block related to the displacement of this point. Okay. Okay. So just a few things. If we follow a process here, we can come up with a free body diagram, and we have to think about the position coordinates, the related the displacements relative to P and the block. Okay. And the next thing is one of the for our power equation, our power equation is just taking a step back and looking at that, the power equation, it's the force dotted with the velocity. Okay. So right off the bat, we have to think we need to know something about the force or the tension in the cable. Okay, so that's the second part here. And then we can use that information, because we're giving information on the velocity, right, 12 meters per second. We can use that to calculate the power supplied to the motor, by the motor, and then to the motor, of course. Okay, So this would be supplied by the motor, and then we can use the efficiency to determine um, what the input power supplied to the motor was. Okay, so the first part what we'll do is we'll come up with some position vectors and relate them. So we have SP will be the position of point P relative to some reference point, and we'll use the pulley, center of the upper pulley, which is not moving, um, as our reference point. And we have SA as our other reference point for our block A. Okay, so in terms of thinking about like okay, so we can look at the position of the cable. This is an L. Looks kind of like a one. Came out in the slide. So this is L. So what it says is that basically SP plus 2 times the SA gives us the length, and it's really the length essentially um, from here down to point P. Okay, regardless of whatever's going on here knows. Um, but what it's really telling you is the relationship between these two. So because we want to come up with the acceleration because that's part of our equation that we need to find in terms of our acceleration of point A relative to point P. Okay, so it's SP plus 2SA equals L. And if we're looking at it in terms of acceleration, it's really the acceleration of point P is related to um, uh, the negative of the other one because it's going off in the other direction. Um, A is going up and P is going down. Okay, so we have point AP plus 2 twice the acceleration of point A. Okay, so since they're going the opposite directions, and well, this is the equation you can come up with, and if you just move this over to the other side, the relationship is, you know, acceleration of A is equal to minus half of P, right? Which should make sense in terms of what it's essentially saying is, A moves half the distance of what point P does, okay, for any point in time. Okay, so we're already given information related to this, right? So going back and looking at the problem statement, what we see is uh, point P increasing at a rate of 6 meters per second squared, okay? So that's the acceleration of point P, and we're going to use that to come up with the acceleration of point A, okay? Okay, looking at the free body diagram and the kinetic diagram, and we got twice the tension here. It's 2T because, of course, we're doing it from point A. It's 2T because we have two cables essentially going in the upward direction. Okay. All right. So here it is, and so here's all the forces involved, and here's the mass times the acceleration. So we just write that out, and of course it becomes 2T minus 50 times 9.81. Here's our weight related to that, and it gives us mass times acceleration. So um, negative, it's in the opposite direction. The 2T is pulling in the same direction, so that is the positive component here. And you could go and solve for T. Okay. Just taking a step back and looking at this, the velocity was 12 meters per second. And as a result, you do the inner product here, and then of course you come up with 4.8 kilowatts. Okay, and that's that problem. Okay, next problem. Okay, so we have a car increasing its speed uniformly from 25 meters from rest to 25 meters per second in 30 seconds, and we have a defined engine efficiency. Okay, so what we're going to look for is the maximum power and the average power supplied by the engine. Okay, so So we'll have to think about that, how that relates to this. Okay. And notice this before as we have the efficiency related to it. So we're going to be using the efficiency for both things. We're going to need it for the maximum power and for the average power. Okay. Related to that. So here's our plan. We're going to follow a similar process as before. We're going to come up with a free body diagram and the kinetic diagrams. Apply any equations that we need, equation of motion, F equals ma, and also the kinematic equation. So kinetics and kinematics. And then, we're going to determine the output power required, and then we can use the engine's efficiency to determine the input power. Okay? And there are two powers we're looking at. We are looking at the maximum power and the average power for this. Okay, so the first part is going through and drawing the free body diagram, right? And then from that, we get our kinetic diagram. So what are the forces that we have? We have a constant force going off to the right of the wheels, forces on all four wheels. We have a normal force and we have the weight. And that force essentially equals will result in giving us an acceleration. Okay. All right. So this one asks the last question, essentially friction in the opposite direction. We're kind of neglecting, or we also aren't looking at it like any wind resistance or anything else that might be impacting this. Okay, so we start off with our equation of motion or kinetic equation. And so what we have is in the x direction, we're going to have our, FC's going off in this direction. And we have a weight. This is the component, the x component of the weight, which here's our angle. So it's the opposite side over here. So it's the mass times gravitational acceleration times the angle, the defined angle that was given, which is just, inverse tangent of this is our opposite side over adjacent side, gives us an angle of 5.71 degrees. Okay. Okay, so the next thing we need is we need to determine the acceleration. And we can use the kinematic equation to give us the acceleration. And, we're given time. It's 30 seconds. We already know that. We know our initial velocity was nothing, was 0 because we were at rest. So all we're going to have is, 25 minus 0 divided by 30 gives us our acceleration. Okay. Now what we can do is we can substitute that in. We know we have our constant constant acceleration in the x direction. We can substitute back into our equation of motion to figure out what that force is, F of C. Okay, so here's our equation of motion, the previous one we had come up with, where we had two unknowns in this equation. So we substitute in for AX, and now we can solve for FC, and here's our force FC. Okay. So the maximum power. So the maximum power, of course, in this case is going to give us when we have a maximum velocity, right? So it's that force times the maximum velocity, which was our velocity, the 25 meters per second at the end of our, after 30 seconds. And our average power output is just going to be whatever the force is times our average velocity, which was 25 meters per second divided by 2. And that gives us the average power. Okay? Well, essentially, it's just half of it, half of our max. Okay? Now, supplied by the engine for both the max, all we have to do is what we did previously, is just to use our efficiency. And our efficiency was 0.8 in both cases, so it's easily, we can use that, manipulate on that efficiency equation in order to solve for the power supplied by the engine, the maximum, and the average power supplied by the engine. And that is that for this section.